The main idea here is that while the planet is in orbit, there's a point in which, from our point of view, it crosses its star. The transit of the planet across the star starts at a first contact called T1, and when it's fully over its surface, there's a second contact that we call T2. Then the point at which the planet is not considered as being fully over the star's surface is called T3, the third contact. Finally, there's a fourth contact called T4, at which the transit is over. Now, the total transit time, as you can assume with these previous explanations, is the time that separates T1 and T4, while the full transit time is the one between T2 and T3. Essentially, these two values can be obtained from the light curve as the star's brightness decreases when the planet does its transition. Now, the passage of a planet in front of its host star, which is called the transit, as I just said, creates what we call a secondary eclipse that blocks a part of the light coming from the star. In our case, the transit of K to 140b creates a depth of 1.6% in front of its solar source, which decreases its brightness. Amplitude radial velocity is defined as the rate of change in the distance between the exoplanet's solar source and the Earth, where the Earth is defined as the observer. Therefore, this value, which is approximately 104.1 meters per second, measures the speed at which the star K2 140 moves away from our planet. The stellar effective temperature defines the amount of heat per unit of surface area of the star. In the case of K2 140, this value is 5,585 kelvins. As for the stellar luminosity, it's defined as the total amount of energy produced in a star and radiated into space in the form of electromagnetic radiation. The value for this particular exoplanet is 3.841 times 10 to the 26 joules per second. Therefore, by combining these two values, we know that K2 140 can be classified as G in the spectral class. These values, as we know them, are pretty straightforward. Therefore, the mass of the star is 1.909 times 10 to 30 kilograms. Its radius is 7.005 times 10 to the 5 kilometers, while these same values for the exoplanet are respectively 2.294 times 10 to the 27 kilograms and 8.861 times 10 to the 4 kilometers. With the known radius of the planet, we can obtain its volume by calculation, which is 2.914 times 10 to the 15 cubic kilograms. Finally, with these two values, it's then possible to determine the density of the exoplanet, basically by dividing its mass by its volume. As a result, the value obtained for this density is 7.872 times 10 to the minus 1 grams per cubic centimeters. Planetary orbital period is the time it takes for the planet to complete a full rotation in orbit around its solar source. By calculations, we found that it takes approximately 6.420 days to do so, which is quite short when comparing it to that of the Earth, which is 365 days. As you can see on this picture, the variable a that represents the semi-major axis is defined as 1/2 of the major axis of an ellipse, on which the planet rotates around its solar source. That being said, it means that it does not necessarily represent the distance between the planet and the star. In our case, the value that we found by calculations was approximately 0.0669 astronomical units. The impact perimeter is the perpendicular distance that separates the path of a projectile and the center of a potential field that an object is approaching. In other words, it's the separation at closest approach when a body of negligible mass passes the star in a hyperbolic trajectory. This value, which can also be called semi-minor axis, mainly depends on both the eccentricity and the semi-major axis of the field generated by the star. In our case, the value that has been found by calculations is 0.814. The orbital inclination measures the tilt of an object around its solar source. The angle itself is based on the value between the reference plane and the plane on which the orbiting object rotates around its source. The value found for this parameter in our case is 86.663 degrees. As for the orbital eccentricity, it is defined as the measure at which the shape of the orbit around its solar source deviates from that of a perfect circle. This parameter therefore plays an impact on the varying distance between the planet and the star, which can then impact other characteristics of life, such as surface temperature. The value we obtain for this is 0.794, meaning that it's more of an oval shape than a circular one. Finally, the habitable zone defines the ring-shaped area around the star. This area is mainly based on its temperature and the distance at which it's sustainable for life. Being too far from the star would result in a surface temperature being too cold, while being too close would result in too hot temperatures. Therefore, when subtracting these two maximums that allow the presence of life, we obtain the habitable zone of the star. In our case, the value we found was approximately 1.508 times 10 to the 8 kilometers. Now the question is there a possibility for life on our planet? So for this, we need to know that the primary factor that normally indicates the possibility of life on a planet is the presence of water in its atmosphere. Basically, an accurate method to determine this characteristic is the use of infrared spectroscopy to look at radial velocity variation in the light spectrum. In fact, since different molecules absorb light at specific wavelengths that may vary from one another, it's therefore possible to determine the composition of the atmosphere by looking at its reflected spectrum. More precisely, when water molecules lose their energy and redistribute it through kinetic energy, they emit photons that produce specific spikes in the spectrum. These spikes, which are essentially broadening of the spectral lines, can therefore be analyzed and associated with the presence of water when it reaches the Earth. However, the relative brightness measured in our case is not part of the infrared spectrum, and therefore the presence of water cannot be analyzed by executing this accurate method. As a result, we have to base our research on simpler secondary factors of life, such as the density, which may indicate the planet's composition, the surface temperature, as well as the seasonal variations depending on the inclinations. First of all, based on its calculated density, which is approximately 0.7872 grams per cubic centimeters, we can assume that K2-140b is mainly composed of gas. This supposition can be affirmed by comparing this value to that of Uranus as a reference. In fact, we know that this planet from our solar system is made of fluids such as water, methane, and ammonia, as well as a small rocky center and a helium-hydrogen-methane atmosphere. However, the considerable difference between these two densities, which are 0.7872 grams per cubic centimeters for K2-140b, as I said, is inferior to that of Uranus, which is 1.27 grams per cubic centimeters. This may indicate that K2-140b is missing a solid nucleus similar to that of Uranus. To confirm this previous theory, we can therefore analyze the exoplanet's temperature to associate some possibilities to the elements from which it's composed. Based on our references, it's said that the calculated temperature on K2-140b is approximately 957.0 degrees Kelvin. Therefore, by comparing this value to that of the Earth, which is 288.0 degrees Kelvin, we can roughly assume that it is at least 3 times higher. Another assumption that can be made is that K2-140b is very close from its solar source, as the brightness was comparable to that of our Sun. As for the planet's composition, we can now say that it is entirely made of gas, since all liquid that matched with the planet density would evaporate at this given temperature. In sum, this information also agrees with the impossibility of life on the planet. Finally, the planet's orbital inclination is approximately 86.633 degrees. This still causes extreme seasons that life cannot possibly sustain. In addition to it, the calculated planetary orbital period, which is approximately 6.420 days, implies that these seasonal changes occur in a very short period of time. As a result, the temperature of the planet suffers important variations as it completes a rotation around its solar source, meaning that life could not be sustained through these difficult conditions.